Okay guys, welcome to our next lecture on the topic of rectifiers. So here today we would like to explore the efficiency of half wave rectifier. So in our previous lecture, if you see this working principle of all type of rectifiers we have done. So now we'll be discussing half wave rectifier efficiency, how we can derive the efficiency for half wave rectifier. So I have pre-filled these things since last video size was a little longer. So let us have a discussion on this. Now how we can find the efficiency of the rectifier? It is the ratio of output DC power. So we are taking output from here across the RL. So what is the power here? The DC power. Because output signal consisting of DC and AC, both the components that we have seen in our previous lecture. So only because of the DC component, what is the power we are obtaining, that is our output DC power. And in the input we are having an AC signal. V in is our AC signal. So input we have the AC. So DC power, output DC power to input AC power, that is the efficiency of any rectifier, not only half wave rectifier. Now here the output DC power, it is given by this equation, I squared DC into RL. So let us call it equation number 2. This is our master equation, equation number 1, and this is our equation number 2. Now here the output input AC power, what we are having, it is I square RMS into RL plus RF plus RS. So this point has to be noted because it is the power supplied to the entire circuit where we have the diode forward resistance RF and the supply resistance, source resistance RS here, RS is involved here. So all the resistance in the circuit we are considering for the input power. So earlier also we have seen this waveform. This is our input waveform, which is sinusoidal in nature. So against the theta axis we have written. So theta axis is extension of time axis because we know theta is equal to omega t. So theta, total angle theta is 2 pi. So one complete cycle is covering 2 pi. So we have 0 to pi and pi to 2 pi. Now half wave rectifier is following, output of the half wave rectifier is following the input for 0 to pi, and from pi to 2 pi it is 0. Okay, so let us consider only one cycle. So this is a pulsating DC, and here we can have the average of the output voltage, so what we call VDC. Similarly it is applicable for current also. So that is also a pulsating DC, and we have an average, what we call IDC or I average. Now since the input is a sinusoidal signal, so let us define it as Vin equal to Vm sin theta, where Vm is the peak voltage. Here you can see this Vm is the peak voltage. So naturally V out is defined only between 0 to pi. So when theta is between 0 to pi, then we have output following input, that is Vm sin theta. Otherwise for pi to 2 pi it is 0. Here we can easily observe. So these are our initial assumptions. On the basis of this we will be finding the efficiency of half wave rectifier. Okay, so these are the steps that we are going to follow to find the efficiency of half wave rectifier. So first step, we have to find the average DC output current. So expressions for DC output current we have to find. Then we will find the expression for RMS current. Then we will find the DC output power by using equation 2 in previous slide that was shown. And then we will find in step 4 we will find the AC input power using equation 3, and finally we will substitute these two in equation 1 and simplify it to find the actual expression for half wave rectifier. So that will be our roadmap to find the half wave rectifier efficiency. So first thing is that finding the average DC output current. Now from where we will get it? DC output voltage, that is area under the curve by base. So area under the curve, we have to find the area under the curve. Here we have to find the area under the curve, and my base is from 0 to 2 pi. So we actually need to integrate it. So integration, so base is my 2 pi, so 1 by 2 pi we are keeping here, and area under the curve we are finding by integrating 0 to 2 pi V out d theta. So with respect to theta we are integrating it, and we are getting it 1 by 2 pi. Now as we have seen, the output voltage is defined between 0 to pi, and pi to 2 pi it is 0, so we can omit this portion. Okay, so we are left with now 1 by 2 pi integration 0 to pi Vm sin theta d theta. So that is equal to, Vm is the constant part, so we are taking out and we are writing it as Vm by 2 pi into sin theta. Integration of sin theta is what? Minus cos theta, ranging from 0 to pi. So if we substitute these limits, what we find? Minus of minus 1, minus of minus 1. So that is eventually giving us 2. So we have Vm by 2 pi into 2. So resulting in VDC equal to Vm by pi. So from here we can find the average current or DC current as VDC divided by RL plus RF plus RS. So that means all the resistance in the excuse me, all the resistance in the circuit is considered over here. So now this value VDC is what? Vm by pi. So we are writing it as Vm by pi. Now Vm by this thing is denoted as Im. So Im is equal to Vm by RL plus RF plus RS. So effectively we have IDC. IDC is equal to Im by pi. So let us call it equation number 4. We will be requiring it later on. Now next step we will find the RMS current. So how can we find the RMS current? So first we will find the RMS voltage. So Vrms is under root. So root, from integration we are finding the integration and dividing it by base. We are finding it the mean square. So mean part we can find, and square means V out square we have to take. So integration 0 to 2 pi V out square d theta. So that is giving us the mean square part, and then if we perform under root we will be getting the RMS value. So 1 by 2 pi, now 0 to pi, because V out for pi to 2 pi is 0. So we are considering it as 0 to pi Vm square sin square theta d theta. So that means Vrms is now under root. Vm we are taking outside, so Vm square we are taking outside. Vm square by 2 pi under root Vm square by 2 pi integration 0 to pi sin square theta d theta. Now what is sin square theta? Sin square theta is 1 minus cos 2 theta by 2. So substitute, let us find first this integration part. So integration 0 to pi sin square theta d theta, that is 0 to pi 1 minus cos 2 theta, we can put a bracket over here. So 1 minus cos 2 theta by 2 d theta. So that is resulting in taking half outside. So 1 by 2 integration 0 to pi 1 minus cos 2 theta d theta, that is giving us half. So from here this is integration of d theta is resulting theta only, and integration of cos 2 theta resulting sin 2 theta by 2, and limit from 0 to pi. So substituting these limits, what we get here? Sin 2 pi by 2. So first for theta we are getting it pi minus 0, so that is pi only, minus sin 2 pi by 2. So minus, if we have a minus over here, we can get a plus over here actually. Okay, so sin 2 pi by 2 and sin 0. So sin 2 pi value is also 0, and sin 0 is obviously 0. So let us omit these things, and we are left with pi by 2 only. So this pi by 2 now will be substituting here. here we will be substituting for this. So result of this integration is pi by 2. So substituting this value over here, what we are getting is Vm square by 2 pi into pi by 2. So pi and this pi we are getting cancelled. So pi and pi getting cancelled. So we are left with under root Vm square by 4. So that is resulting as Vm by 2. So VRMS value is Vm by 2 for half wave rectifier. For full wave rectifier it will be different. So differently we will have to find it separately. Now IRMS is what? VRMS divided by the entire resistance of the circuit. So that is RL plus RF plus RS. Now VRMS we have already found Vm by 2. So we will put Vm by 2 over here, and this is resistance we have, and we know that Im is equal to Vm divided by RL plus RF plus RS. So we can substitute this part with Im. So we are getting IRMS equal to Im by 2. So these two things we have found. Now next step. Now one thing I should tell you, that finding the RMS value of current may be optional during your examination, but obviously it will depend on the individual faculty. But most of the cases directly students are allowed to take IRMS equal to Im by 2. Okay, so it may not be mandatory derivation, but try to derive this part. IDC you try to find by deriving. So if you practice by deriving, you need not to remember it, you need not to mug it up. It is just the process which will follow. So just follow the process, outcome will automatically come. Now next point is finding the DC output power. So DC output power in equation 2 we have seen, that is I square DC into RL. Now DC is what? IDC is what? Im by pi. So Im square by pi square into RL. Now Im, what we have seen? Im is Vm by RL plus RF plus RS. So square of that we are putting. So effectively what we are getting, PDC is equal to Vm square into RL divided by pi square into RL plus RF plus RS. So let us square of that. So let us denote it with equation 6. Similarly we can find the input AC power. So that in equation 3 we have seen PAC is equal to I square RMS into RL plus RF plus RS. So that is eventually giving RMS equal to Im by 2 earlier we have found. So we are getting it as Im square by 2 square, that is 4. So Im square by 4 into this resistance part. So we are putting this resistance part. Now let us substitute this Im in terms of Vm. So earlier also we have seen Im is equal to Vm divided by RL plus RF plus RS. So this value we can substitute here, and by simplifying this we are getting average input AC power as Vm square divided by 4 into RL plus RF plus RS. So this value we are getting. So in equation 6 and 7 we are getting the output DC power and input AC power. Now let us substitute from equation 6 and 7 to equation 1. So this was our equation 1, where we have found efficiency is equal to PDC divided by PAC. So substituting those values from equation 6 and equation 7. So what we are getting here? So Vm square we can cancel out here, and also here we have the square term and we have this term, so we can cancel it. So we are left with 4 by pi square into RL divided by RL plus RF plus RS. So if we take RL at the denominator, we are left with this thing, 1 plus RF plus RS divided by RL. So this term we are having. So now if we calculate this, 4 by pi square approximately we will get 0.406. So 0.406 divided by 1 plus RF plus RS by RL. So that is the expression, that is the final expression for the efficiency of a half wave rectifier. Now interestingly, the load resistance is generally much greater than the diode forward resistance and the source resistance. So if we consider this, then this term will be tending towards 0. So we can ignore it and we will be left with eta is equal to 0.406. So what we name as eta max for a half wave rectifier, maximum efficiency can be 0.406, or if we convert it to percentage, that means we will get 40.6% efficiency. So half wave rectifier efficiency is not up to the mark. From this we can find out, and that is why it is seldom used, the half wave rectifier. But we have an advantage, that is it's a very simple and basic circuit. Obviously due to simplicity, only one diode we are using, so it is very much cost effective. So that is what we can conclude from this efficiency derivation. So we end here. Thank you very much. So in next lecture we'll be discussing ripple factor and some other parameters of half wave rectifier.